So, I don't know about you, but personally, I've always been interested in engineering ever since I was a small child. And for me, the application of materials technology to solve construction problems is a fundamental part of being an engineer. And if we're to be halfway good at our job, then it helps if we understand a little bit of the background to the processes and materials that we use in our everyday occupation. So if we consider concrete, I suppose the first question to ask is, what does concrete actually mean to you? It may be that for you, concrete is simply well-graded stone that's held together with a binding agent of some description that gains strength and can be used as a building block for something or other. In which case we can trace concrete evolution in that context back probably about 6,500 years to, of all places, North Africa. And we see examples of this throughout Middle Eastern civilizations. We see it in the ziggurat, for example. We see it in the construction of the pyramids, and so on and so forth. But actually, to all intents and purposes, the use of a hydraulic binder to bind together a well-graded aggregate material can probably be traced back to Romans, and at around about 200 BC as a process of developing stone blocks, easily formed shapes, etc., using a combination of either volcanic ash, a reactive volcanic ash, a particular grading of pumice, or indeed a reactive silica type material, which I have to say the Romans did have in abundance in certain parts of their empire. And the Romans were able to produce some fairly impressive feats of engineering, including, for example, the Pantheon dome, the dome of the Pantheon in Rome, about 43 or thereabouts meters in diameter, clear span, a plain concrete dome. Maybe looking at that and think to yourself, well, what's the big deal? Well, go back 2,200 years and say to yourself, what's the big deal? Well, that's an impressive feat. That would actually tell you, having been taken to Rome, following an altercation in wherever it was you were born, that these are people not to be messed with. They are serious engineers, they're serious builders. These are civilized people. Unfortunately, with the demise of the Roman Empire, we see a demise in the use of concrete technology and the use of concrete materials, generally speaking, until around about the 19th century, when an interest was developed in concrete throughout France, Germany, America, and the UK as a means of reducing the cost of construction rather than transporting big pieces of stone from A to B and then jointing them together with some kind of a cementitious mortar material, such as a lime mortar, for example. Perhaps it would be easier just to take the cheapest locally available material and bind it with a hydraulic binder and cast it into a shape. Well, this entire endeavour was assisted greatly by the discovery of Mr. Aspinall that Portland cement can indeed be made by burning clay and gypsum at a high enough temperature and grinding it up and using that hydraulic reaction to form a stone material that rapidly gained strength and was actually significantly capable in terms of compression. By the mid-19th century, we begin to see a development whereby plain concrete is being reinforced on the surface that is, should say, subject to flexure with, for example, mild steel. And this is great. This is quite a development. We're now talking about a composite material. We're talking about concrete and a reinforcement material that enables it to become not only strong in compression, but reasonably strong in flexure. And of course, the development of mild steel into high tensile steel simply reduces the amount of concrete that's required and indeed reduces the amount of reinforcement that's required. And by the 20th century, we're beginning to see an interest expressed in the use of concrete as a composite material in conjunction with fibres of some type or other. Initially, waste byproducts from some steel milling operation, etc., etc. But eventually culminating in the use of high tensile drawn wire. And of course, we also see the development in the 20th century of pre-tensioning and post-tensioning. And this is not particularly new stuff. I mean, this has been around now. Post-tensioning, for example, has been around for 900 years. And it's a very, very interesting way of increasing the strength of concrete in flexure by simply stretching the reinforcement, anchoring it, and maintaining the concrete in a state of permanent compression. And of course, by the 21st century, we are starting to see the development of composite materials that can be considered largely isotropic. In other words, concrete materials that are saturated with steel fibers that are able to control the effects of shrinkage, all of which leads to the use of less materials and a faster and smarter method of construction. So far, so good. So what does this mean in terms of how we build things then? Well, if we consider, as an example, bridging a gap, there's always been the option to fill the gap and generate a causeway. And if we don't have materials of the right shape handily available, we could always start to use a concrete type material, a cementitious type material, to fill that gap, which is great. Unfortunately, of course, you'll tend to get, in the case of a gap such as this, a water build-up, for example, on one side or the other, and it's not a particularly strong structure when subject to hydraulic pressure. And of course, as we all know as engineers, there is nothing more destructive in the natural world than water, or possibly compound interest. However, there is nothing to stop us from bridging a gap, and there's nothing to stop us bridging a gap, if we wish to, with plain concrete. It's just that, as a rule of thumb, whatever the width of the gap is, that width plus a little bit will be the depth of concrete that we use to bridge it. However, if we use steel bar, we can actually start to reduce that section depth of concrete. And if we put that steel bar into tension, then we begin to reduce that section depth even further. And this is before we start looking at cable stays and so on and so forth, and as a means of suspending bridges. So push all that off to one side for a second. There is a method to my madness. There's a reason for mentioning bridging gaps. Because, of course, for most people, if you were to bridge a gap, you would say, well, okay, we're going to bridge that gap, put aside the formwork issues, because that's going to be quite significant. We're going to place this concrete, yep, and we're going to place these steel bars, yep, right. Well, the steel bars are only about the length of a truck bed, 12 metres. Okay, so we've got a gap of many times 12 metres. How do we tie all that together? Oh, we use soft anneal tie wire, of course. That's great. And what does that do? Well, it does the square root of nothing, actually, to the flexural strength of concrete, because what we realise is that the failure mechanism for a beam in this type of context is actually nothing more than a problem of shear, some microns away from the face of the steel, in fact in the steel and mortar interface. And what does that mean? Well, it means that if you look at a bridge of a significant gap and you look at the 12-metre long bars that are laid across that bridge, they're held together with nothing more than lap length. And if you look at them from far enough away, they look a little bit like very, very small things. In fact, they look a bit like fibres. And in fact, the beauty of fibre in concrete, particularly high-strength drawn steel fibres, is that you can saturate the matrix of the concrete with them. Okay, so that means as a crack forms, it travels through the mortar matrix until it hits a piece of fibre and then it's arrested, and you develop another crack somewhere else. Many, many cracks. Okay, so what you're saying then is that a big bridge is nothing more than an exercise in trying to understand the concept of steel fibre reinforced concrete. Yes, that's exactly what we are saying. Because, of course, as we develop the use of concrete for floor slabs, we begin to see that For ground-bearing applications, fully loaded, and particularly in the context of a modern distribution centre, for example, the part of the slab that's under the most pressure is actually at the bottom of the slab. That's in tension. The top of the slab is usually in compression, although of course if you've got a block-loaded slab, i.e. a significant UDL, and you've got gaps between those loads, you can get a hogging moment in the aisles. Okay, so what's the answer? Well, we can use mesh fabric. But what does the mesh fabric do? Well, it increases the flexural strength of the concrete on the side that it happens to be up against. Okay, happy with that. But actually, isn't the purpose of the mesh fabric really to control the joint behaviour? What do you mean? Well, for example, if we were to just leave that mesh fabric in that concrete over a large area, laid extremely thin, we're going to get a huge reduction in volume because, of course, concrete shrinks. It's what it does. It uses a proportion of the water in the mix for hydration purposes. The rest is free water, and we get a reduction in volume. So we're going to get cracks. Okay, so what's the answer? Well, we put saw cuts in. Okay, so what do the saw cuts do? Well, the saw cuts relieve the shrinkage stress where we put them. In other words, we're forcing a crack to occur where we want it to occur. Okay, is there a problem with that? Well, in many cases, no, not really. But actually, in distribution centres, that's quite a significant problem because these are subject to high traffic intensity. And those forklift wheels, they're not softened in any way, shape or form. They're normally quite hard, quite durable. And as they rattle over a joint, a saw cut induced joint, so they'll set up a bit of a shock wave, which in time will result in arris damage and the breakdown of the slab. Okay. And then we've got to say to ourselves, well, what about on pile supported slabs then? Because whilst mid-span we are in tension at the bottom of the slab, over the pile we've got a hogging moment, and they can be quite significant. So we're going to need more reinforcement there, and now we're going to have to start considering shear. And it all starts getting really dreadfully complicated. Well, it does. Of course, we could consider a post-tension floor slab. What's the point of post-tensioning? Well, post-tension means that we run a series of tendons throughout that concrete, left to right, far to near, however you want to put it, and we put those tendons in an arrangement such that when we stretch the tendons and lock them off, that concrete is in permanent compression. Bit like a drum skin when you think about it. I don't know if you've ever actually rattled around with a drum. For now, I had a set of Mexican bongos when I was a kid. They were great fun. They worked. It didn't matter what you did to them, you could pat away at them all day long. Because that drum skin was in tension, it would just give a satisfying noise that drove my parents insane. But you know what? Unfortunately, one day, I slackened off the drum skin. And you know what happened? I put my little hand through it. What's the relevance of that? Well, if we actually post-tension the concrete as a flat plate forming a slab, we make it very, very tough. We make it very strong in flexion. We actually give ourselves a bit of dimensional stability, and we've certainly got shrinkage control. We don't have the opportunity to develop shrinkage cracks because that concrete's in permanent compression. And we increase the load capacity significantly. Which brings me on to the Primekks floor slabs. Now, interestingly, Primekks floor slabs are predominantly steel fibre reinforced. So what do you think? That's old hat. We've been doing that for 30 odd years, nearly 40 years. Well, we have, that's right. And we've been producing joint-free floor slabs for probably about 35 to 40 years, where the steel fibres are incorporated into the concrete in such quantity that they control the effects of shrinkage. So instead of having to put a saw cut in at about every 6 metres or so, we can let the panel size increase to about 40 metres or thereabouts, and that concrete will simply reduce in volume, and that's great. And we don't need to put a saw cut in. That's fantastic. But the construction joint is actually quite wide. Can be quite wide. That's a bit of fun. The shrinkage is something in the region of 1 to 2 millimetres for every 10 metres of slab span. So if we have two 40-metre panels side by side, the joint in the middle can open up anywhere from 8 to 16 millimeters. 20 millimeters is not uncommon. That also is a function of the aggregate grading and the aggregate type and so on and so forth. However, PrīmX has, fortunately, been part of a European research program for the last almost 30 years, developing what we call second generation shrinkage compensating materials. What exactly does that mean? Well, if we think about the hydration process of concrete itself, we've got cement, we've got water, we've got sand, we've got coarse aggregate, we mix them all together, and a chemical reaction occurs with the cement paste, which starts to form things like trilume, silicate, etc., 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 and all of this stuff reduces in volume. It acts like shrink wrapping. It pulls everything nice and tight. It's actually where we get our compressor strength from. A shrinkage compensating admixture will actually work by a delayed process. As the concrete itself starts the shrink wrapping process, as the cement mortar does its bit, it's reducing in volume, shrinking, pulling everything tight. So we have a delayed reaction and the formation of expanding minerals, ettringite particularly, which actually starts to force the concrete apart at a microscopic level. Over time, this ettringite in turn changes its state and reduces slightly in volume. Effectively, we have almost like an accordion effect. The concrete starts to strengthen, reduces in volume, starts to expand slightly, starts to reduce slightly. But the net effect after about 14 to 20 days is that the concrete is around about 300 to 400 microstrains larger than when it was laid. And what does this mean to us? Well, to all intents and purposes, we have zero shrinkage. And that means it's a dimensionally stable product. It's actually not going to change significantly after, say, 18 months or 24 months, as concrete does. Drying shrinkage can take place in normal concrete for about 24 months or thereabouts. Interestingly, as the mortar starts to expand, because the ettringite is pushing it apart, it actually puts the steel fibre into tension, stretches it, and locks. And that places the concrete in a state of permanent compression. So our reinforcement, which is evenly distributed throughout the concrete, throughout the mortar matrix, from left to right, near to far, top to bottom, doesn't matter where you look at it, you'll find the same amount of reinforcement, and you'll find the same process going on, which is the reinforcement being stretched, locked, and the concrete placed in permanent compression. Well, that's actually significant. And actually, it means that the Primekks system is, I suppose you could think of as post-tensioned or pre-stressed. The analogy is yours to determine for yourself, really. Personally, I think of it as post-tensioned. It means we've got a dimensionally stable material. It means we've got something about, around about 2.5 times stronger than a plain reinforced concrete. And it doesn't matter where we go in that slab, if it's cured properly, and it's designed properly, and it's laid properly. This is a material that means you're probably going to get away with using about 40% less than you would for a plain reinforced concrete. So far, so good. But it does mean as a company, PrīmX has to consider the fact that this is not something you can just let loose on the industry. We have to regulate it. We have to take care of the material itself to make sure that in the first instance, the concrete mix design that we come up with is bespoke to that area. So in other words, we're using the materials that you have available locally at the area, at the source, at the point of production. We're testing those in a laboratory. We're working out exactly the proportion of shrinkage compensating material that we need in there, and the type and proportion of steel fibre that we need in there to give us the mechanical properties that we need to satisfy the design. This is all backed up by full-scale testing and the use of our proprietary quality control system throughout the entire process, which enables us to give a test-assisted production on a day-to-day basis on the job site. We can talk to the laboratory about any issue that we have on site, change in ambient conditions, change in cement type, any issues that affect the batching of the concrete, really. And we can have an answer there and then that's informed by concrete technicians who are trained specifically for this process. Everything that we do at PrīmX is a research-based activity. We would rather interpolate for accuracy than extrapolate for effect. PrīmX is one of the very few companies in the world that will design and build your industrial floor slab that actually has a research and development centre. And this isn't something that's lip service to promoting what we do ourselves. This is a research and development centre that actually assists with EU research projects. We work at CERN, for example. Oh, maybe I couldn't say that. Who knows? We'll see if I get away with it or not. However, we still have to fit PrīmX into the design codes and standards that exist. So how do we do this? Well, that's perhaps not as easy as it seems, in the sense that you are aware there are no design codes for ground-bearing or pile-supported floor slabs. They don't exist. We have design codes for structures. We can design and build elevated slabs with design codes, and we can use linear elastic design models if we wish, which of course means that the concrete is not going to crack. We could look at technical reports such as TR34. And TR34 is actually quite kind to PrīmX in the sense that it makes it very clear that post-tension concrete exists and can and should be used. In fact, TR34 makes it very clear that if you, as a client, want to have a crack-free floor, then the only real practical alternative you have to plain reinforced concrete is to use a post-tension system, such as PrīmX. We can design to ACI 544, which is a very interesting document put together by a fascinating institution, which at the end of the day is all peer-reviewed. So it carries, to my mind, the same weight as a design code. And in fact, if we consider the full-scale destructive testing we do and the laboratory testing that we do at PrīmX, it is very easy to see that PrīmX provides test-assisted designs that are fully compliant with BSEN 1992. And of course, we will comply with any industry requirement for the design of innovative products of composite materials, because we are as interested in developing our system and we are as interested in promoting best practice as any other competent professional company, probably more so. So what benefits does the PrīmX system provide for you as the client, as the end user, as the contractor? Well, it's actually very simple. If we can eliminate shrinkage, which we do with our chemically post-tension concrete, we're actually going to eliminate 90% of post-construction defects. Can we prove that? Heck yeah, you only got to look at our defects bill. It's a phenomenally small amount. We've probably got the smallest defects bill of any construction company globally. We can provide you with dimensional stability for the structure, whether it's ground bearing, pile supported, composite, elevated, roads, bridges, basements. It's a watertight and gas-tight system. We provide a lifetime flatness for slabs. And the higher load-bearing capacities that we have, because this is a post-tension product, results in a significantly reduced section depth. So what? Well, that's got a profound impact on our carbon footprint. If we look at cement replacement materials in conjunction with our post-tension design methodology, we can reduce the carbon footprint of your floor slab by up to 70, maybe even 80%. That means we are a very sustainable product. There is absolutely no reason at all why you wouldn't consider having Primekks on your team. Anyway, I think my time is coming to an end, and I'm looking forward to the questions that you're going to ask me and the interrogation you're going to provide me with, and maybe, as all engineers do, we can have a little bit of a chit-chat, and I shall see you shortly.